Hello everybody, let's talk a little bit about the Simulink PX4 Autopilot input-output framework that I wrote. And just to give you a quick overview of what this thing does, it's essentially a generalized framework slash integration package slash bug fix for the MATLAB version 2023A. That's using PX4 version 1.12.3. Just to essentially, we use that for all of the research activities that we have in the lab, as well as for the additional projects. But just two quick simple examples are like the quadcopter that we're flying in the lab, and some of the outdoor flying that we are doing with the tilt wing that you see on the right. So it doesn't necessarily matter what you're going to be flying, because this is more of a very general sort of framework to allow getting all of the data in and out of the PX4, as well as communicating that to and back from the ground stations or station. So in essence, what we're talking about is, you can think about three different systems that we are trying to consider over here. Is of course our PX4 Autopilot, which is essentially our firmware that is getting compiled and burned and uploaded to the Pixar Cube Orange that's shown basically on the very topmost big block over here. That is running all of the subsystems of the stock PX4, which are like the Mavlink communication state estimator, or any other module that you can think of, all of the drivers. It's relying on its own internal UORP structure, so you can read all of that about the documentation for the PX4. This is just assuming, I'm here going to assume that you already are familiar with the PX4. You just are looking for a way to integrate this with the Simulink for the older releases. And again, the more recent MATLAB releases may actually introduce this as a bug fix or some similar version that is no longer requiring any of these modifications. So I would recommend first checking a more recent MATLAB release before diving into this in more depth. But the idea here is that we have a Simulink deployed flight control system. So it's basically literally your Simulink control system model that you want to cogen and deploy and run on board and use the existing capabilities of your PX4 Autopilot. You're going to have a whole bunch of peripheral sensors that are either built in or are external, like LiDARs, receivers, obviously your actuators, whatever those are, as well as your communication modules. All of that is more or less managed automatically by PX4, and there's so much more to explain that is already outlined in all of the tutorials that PX4 has and the documentation out there. So what we're going to focus on is a little bit more specific example where we consider two different ground control stations slash softwares. We want to not just deploy the control system from the Simulink, we also want to support some ground control station capability with, for example, joysticks or basically a secondary Simulink model that is serving as a monitoring station at the same time as for example, a relay or I guess a controls panel slash control input model for your joystick, or basically your pilot inputs. That can be anything. It can all be done in Simulink in a very convenient manner. So we're going to be talking about how that is integrated, as well as, for example, you can have additional software slash hardwares running on the same machine or on a separate machine that also wants to talk with the vehicle. And for this example, we're using a small Raspberry Pi based ground control station just as an example, because that can be used for a variety of purposes and requirements. So this is all based on the two repositories that I have uploaded, which is the PX4 Simulink input-output framework, which essentially contains all of the firmware modifications that go into the PX4. that allow all of this, as well as an example for a tilt wing that I'm going to be talking today, which is basically the Simulink model with this input-output framework integrated as part of the Simulink model without the control system. All right, so let's scope a little bit more into this part, the Simulink deployed flight control system, because that's where probably the most important pieces from the user perspective are. So if you wish to integrate your control system, you probably have done already some prior, simulation work, some early validation and testing. You basically have a model, right, with certain number of inputs and a number of outputs. More likely, again, if it's a control system, you're going to have your states, control inputs, and then you have your actuator outputs. So I have just generically added it at the center of this topmost block, which is basically we're doing some work, right? We don't actually care for anything that I'm presenting here. It's not that important. What you're doing is as much as how do we get all of the information for that model to run successfully. So everything here, circled in blue, all of these blocks are actually Simulink modules. Sorry, not Simulink, PX4 modules. So in PX4, you have what they refer to as modules. They are basically separate, not really applications, but parallel processes that are executed by the PX4. They have their own update frequency. They run asynchronously, and then you have this UORP framework to talk and exchange information between all of those modules. So in Simulink basically implements already an interfacing layer, which implements these blocks that are called UORP read and UORP write to get all of the UORP topics, which are PX4 data structures, essentially. They contain all of the needed information. You can read those and write to those from Simulink, and that's how you get this talking going between the PX4, so everything below, and your Simulink code over there. So all of this all together at the end of the day gets the Simulink part gets automatically code-gen or generated into C, and everything together with the PX4 firmware is compiled and burned on the PixHawk board. So this is all technically at the end of the day is one PX4 firmware, just like we're going to replace everything related to the control system, and that's done already automatically out of the box with the UAV toolbox. So this orange block is what we are going to inject instead of the stock PX4 controller. So the key part again is these inputs, outputs. So we talked about UORP topics. There are also parameters. So PX4 implements its own parameter framework, and the main difference between all of these UORP reads as well as and parameters is that the UORP reads internal memory in the PX4, and what's important about it, it's considered to be real time. It's basically as fast as it can only be. It's on demand. But then there is a lot of work that went into making sure that there is no conflicts between parallel processes running, that we can access that data as fast as possible. Parameters, on the other hand, are more of a less critical piece that is easily exchanged between the PixHawk, the board itself, and the ground station. You see that's what you see in the Q-Ground Control or Mission Planner, depending on what you're using. And those parameters are assumed to be more or less not fixed, but they can be configured remotely. But we assume that these are not our sensor inputs or anything that is going to be changing at a very fast frequency. So there is a separate way to retrieve those. In Simulink, there's again a built-in block called read parameters. So you can retrieve those, and that's how we are going to import some of the settings into our Simulink model that we don't want to, when we change those, we don't want to recompile the entire module. We have a flag that changes some of the behavior. that is important for some of our testing, and of course we wouldn't want to spend a lot of time recompiling just to change that single flag. So this is what parameters are, what they're used for. All of your breeds are reading topics that are fixed in their structures, but the data fields are being filled in by the PX4 all the time, or we're publishing them, or I guess. So there's this a concept of publishing and subscribing. Subscribes essentially means that we're reading from the data structure without modifying it. Publishing means that we are posting new data. We're filling in the values for the data structure. So we're modifying it. And these two processes are essentially read and write. They're implemented inside of these UORP reads and writes. In the PX4, the way it looks like, you literally have UORP subscribe and UORP publish. Methods for your UORP objects, which you can call and then fill in all of the information, but we can talk about this later. So the important part is that for this framework to work correctly, there is a new module that was implemented and provided with this package as part of the PX4 upgrade. It's the Simulink control module or modification module, which essentially does all of the low-level data handling to incorporate everything that we're going to be talking today. And primarily what it's doing is it's obviously accessing internal parameters, and we were trying to resolve some of the problems with how many topics we can read and write from the Simulink. And it was found out that basically the easiest way to do it is to limit it to 2 or basically stay under 4 topics. So essentially a lot of this data sort of packing and depacking I had to implement. There's this new message called Simulink inbound. That's a new UORP topic that we are subscribing and reading from the PX4 and Simulink. That contains all of our control inputs as well as all of the state estimation data that we need. Then when we are done with all of the work that we're doing in the Simulink, we're publishing technically a single topic that consists of all of the actuator outputs, and then we also added an extra one just to accommodate all of the extra data that we need to relay back to the ground for, again, ground station monitoring, displays, or just maybe some post-flight analysis. And essentially we're trying to do, so again, as I mentioned before, all of these topics are considered to be real-time, so we can monitor our flight states and all of the information as we are flying and as we are doing the flight testing. There's one key topic that must be published for everything to function called Simulink outbound, and this is with respect to, again, this model on the top. And then there are 3 more that are not actually being used by this framework for anything except just these are placeholders to relay any kind of data back to the ground. But we're not essentially relying on any of these 3 for anything important related to correct functioning of this framework at all. We're basically relaying them. All right, so, and then the Simulink control module, what it does, obviously it reads all of the internal states and, I don't know, data from the PX4. We can loosely generalize them as all of the manual control inputs from your RC or maybe from your ground station joysticks. We also read all of the state estimation data, and then we do read all of the data related to communication. So talking outside of the board, so outside of the PX4. And at the end of the day, what matters for us is that we are going to be publishing this actuator output servos. It's a new message, not previously added as part of the stock PX4. This is reserved exclusively for the UAV CAN driver that has been upgraded to basically support this entire framework for regular single shot or PWM servos and ESCs or electric speed controllers. And we're going to talk about all of this a little bit more in depth on the next slide. But let's just quickly again talk about the Simulink and the way it looks like in the Simulink, just so you get familiar with it. So this is what you download with from one of the repositories that were posted previously. So you are gonna see this top level implementation. This is exactly the diagram you've just seen, but this is in the Simulink itself. So we have this block that essentially all it does, it calls this PX4 URL read, and we get all of the data we need. Again, this is from PX4 firmware into Simulink model. And then on the right, you have the same blocks or similar, where now you are sending everything back to PX4. So what's important here, there is no communication or direct talking with the ground or anything outside of the PXOC board itself. We are purely communicating with the PX4 firmware, and everything else is handled internally within the firmware itself, just to remove any kind of need for synchronization or, I don't know, excessive code for different command handling or anything else that shouldn't really be part of your, I guess, control system, quote unquote. Then yes, there is this block, which is basically, again, calling the parameter read function implemented in the Simulink, and that just imports a set of parameters that you need for your control system to function. So if we step into this block, so all of this data is basically raw, except for probably parameters. Once we step into the middle block, what we need to actually do before we call our control system that actually does something that we're interested in, there is this deparsing or decoding part happening on the left, and which is essentially taking care of all of the proper data structuring, labeling, and making sure that everything is well commented. And basically what it does, we're just making sure that the information that we retrieved from the PX4 makes sense and is simple to use for the rest of the model. Then we do the exact thing in the reverse. We take the Simulink data that we're interested in, and we are encoding that into the format assumed by this input output framework, and we are sending that back to the PX4 in the appropriate format. Again, all of this was done to limit the number of topics we have to publish or subscribe. So this encoding and decoding is necessary. This is actually the exact same process that we can replicate these blocks. As you can notice, these are reference subsystems. We're actually using this on the ground station. It's the exact same, but I will cover that in a separate video. All right, so this, again, everything that we send back is more up to you. It can be anything. The important part is that we obviously want to send actuatory commands. This is the only mandatory part, and the instructions and everything are outlaid in the documents, but I'm going to quickly go over how that's done so there is no ambiguity in that. Yes, so let's first talk about this block over here. So we are getting all of the data from the PX4. Really, the way it looks like, the important part is we have part of our message is related to control inputs. So everything related to manual pilots, inputs, and some extra parameters. So the way I was implementing it is we have a data structure in the PX4, which I reproduced here using a bus, a Simulink bus, which, again, you can modify some of the defaults that are set in there, although I don't think any of that really has to be changed at any point. What's important that this structure remains the same, and it has to be synchronized with the PX4. If you ever changed anything in the firmware related to the communication or I guess control order or control vector that you're sending, you would have to modify everything upstream, which in this case is the Simulink model. But basically here what you see is a simple bus assignment block. So this is just initialization, and then we are going to fill in all of the data from that we just read from the PX4 and assign it into the correct placeholder. I mean, it's very straightforward. Pretty much everything complicated is done in the firmware. So here it was made to be as simple as possible. Similarly, for all of our inputs, we also get states, right? We get all of the states, and the way it was structured is similarly, we're creating a bus input, or I guess bus, Simulink bus, because we can just label all of the data. If we double click on this block over here, we can view all of the data that comes in, and it is all labeled. And I chose to label it with respect to the UARP topics that the data is supposed to be coming from. So I say supposed to because there is some logic that we'll talk about later, probably in a different video. No, actually at the end of this video, that changes which topics we're using for all of that data, but that happens internally in the PX4. Here, it's just for your own convenience, like if you're used to using your blocks directly and reading a specific topic from the PX4, you should have no problem interpreting what these are. They don't have all of the data, they only have the one, I guess the fields that were labeled as, I guess, important, or the ones that are actually useful. So for example, for vehicle acceleration or airspeed, you see there are only a couple, like there's only a single field for the acceleration being sent, because the rest is not really relevant for us. And then the same thing for all of the other topics, but it should have all of the important information. If not, all of that can be added in the firmware, and then again synchronize here with the Simulink model, but that has to be done manually. Alright, so let's talk a little bit more about these, I guess, topics that I mentioned multiple times. These UARP topics that we have, or I have added into the firmware. And basically there are four, or I guess there are four, three topics plus three more that are optional / I mean, they are based on demand. You don't really need to use these at all. But the most critical, the essential ones are these three that are related to getting data to and from the Simulink model. So the first three on this slide. So the very first one, this is what I refer to as the Simulink inbound, and this is basically the Simulink input vector. So we are treating it as data that is being read by the Simulink. Again, this is agreed upon. There is nothing to actually enforce that, and the structure of that is fairly simple. The first 18 it's basically a vector, right? It's a vector of 58 elements, all floats, all of the same data type. The first 18 of that vector are allocated and basically reserved for control inputs from the pilot. The rest of the elements are for whatever states that we want to send from the PX4. Currently, we have a total of 36 states sent from the PX4. And there is basically 4 unused empty slots that can be filled with something that we just forgot about. This is basically future expansion in case we need that. Then there is an additional, I guess, also optional topic. It's called Simulink inbound was appended with control. So this is not used primarily for like flight experiments. This was implemented, essentially it's a copy. It's the exact same structure, the exact same topic as on top. It's the same Simulink inbound, but this is related for control applications when we're trying to do hardware in the loop stuff, and we want to generate all of the states and control inputs in replacement from those generated by the PX4. So that can be configured separately. Technically, this is also optional. when we're flying, we should not be using the Simulink inbound control message, although it does allow you some of the optional stuff to be assigned to it. The way it's used in flight is we don't actually assign any states. We don't care. These can be anything. We're using all of the states and inputs from this message on the top, the Simulink inbound, just like shown on this diagram over here. There's only a single topic being read by Simulink. There's no logic in the Simulink that decides which topic it has to read from. And then if we need a secondary control input, for example, from GCS, like a joystick or whatever, or multiple joysticks, we send over this control input, the Simulink inbound control message, and we tell configure PX4 itself the Simulink control module. So this guy, Simulink control module, we configure that to take data, control related data, and use that instead of the one provided by the PX4, and paste all of that into the Simulink inbound. So again, the Simulink still reads the exact same data. It doesn't care where it comes from. This question of where is all handled internally to the PX4 inside of this Simulink control module. All right, but for now, let's just focus on this over here on the top, because this is more important than anything. This is the structure of all of the inputs that come in, and if we are using something internally inside of the PX4, again, it makes no relevance for the Simulink model, because it's always reading this Simulink inbound topic shown on the top of this slide. All right, so when we are writing our outputs from the Simulink model, we use the Simulink inbound topics. Outbound topics. And the structure for really, if you don't care as much about getting all of the possible data from your control system, all of the intermediate states, or whatever the calculation that you're doing, you probably only need this first. A Simulink outbound, you're going to write your actuator commands from the Simulink model, which are essentially the first 16 entries of this vector, which is again the same size, 58 as in total. And then you're going to keep the other 42 elements either empty or assigned to 0. That doesn't matter, because again, they're not used by anything inside of the PX4, neither Simulink control mod or anything else. Everything after the 16 actuator commands is purely for your own purposes. If you want to relay the Simulink outbound back to the ground station, or log that data, or do whatever you want with it, this is not going to affect anything internally to the PX4 or its functions. Only these first 16 entries. Similarly, or I guess as an extension, if you need to send more than 42 data entries, there are these optional topics that you can write to, called Simulink inbound appendices 1, 2, or 3. All of these are actually not even being accessed by anything internally. I'm talking about like PX4 again, in a way where I'm not even looking into what is this data inside of this, just like I'm not looking here at the entries after 16s. Here, all of this is just being bluntly forwarded back to the ground if it is again enabled and configured to be forwarded, which by default it's not, because you would have to configure that, but we'll talk about that later. All right, so let's talk a little bit about why this structure was picked. So in reality, in the firmware itself, what you see is, technically in the PX4, in the Simulink model 2, what you're doing is you are going to access what's called a debug array, or in Mavlink it's referred to as the debug float array. And again, there is a corresponding topic inside of the PX4 called debug array. So these are two different things. That's very important to understand. There is a debug array that is like here, shown on the bottom. This is literally a snippet of the PX4 firmware, and that's internal to the PX4. All of the UART messages, again, are to exchange and share information between PX4 modules. But if you want to get data outside of your firmware, you would have to package that and use Mavlink. Mavlink is basically a protocol. You can read about that, which I'm sure you have already used it plenty of times. But a lot of the Mavlink messages and UART topics are essentially the same thing. I mean, they are called very similarly. They have the same entry sometimes, or actually oftentimes. The UART topics just have extra fields related to PX4 functionality and how the Mavlink message that corresponds to this UART topic has to be interpreted internally. Again, just an example, any Mavlink message, and this is again just taken from the Mavlink documentation, you have a whole bunch of communication related entries like your start bytes, end bytes, signatures, checksums, message IDs, system IDs, component ID, everything related to communication and addressing and forwarding, and related to making sure that your data is not corrupted. So that is all handled by Mavlink. That's just out of the box. I kept using that I guess framework, structure, and protocol all together just because it's already ensuring that you don't have any corrupted data coming back on your GCS or going to the vehicle, as long as the data itself that was encoded, it was encoded correctly and it was parsed correctly. If there is some corruption on the way, you know how that works. That just gets discarded because the checksum doesn't match. But yeah, so what we're talking about, so what we just saw on the previous slide was the Simulink inbound control, and outbound messages, which are technically, I'm going to be calling them messages / UART topics because they're pretty much the same, and referred to as messages or topics by PX4 and interchangeably, but the Mavlink messages, they are not topics. Those are just literally messages and protocol that is external to the PX4, and we're just using that for external communication. All right, so this payload part of any Mavlink message is what we care about, and specifically for all of this internal communication, again, for all of these messages, we are using the exact same UART topic / message. It's called debug array.message. It's literally a file. There's a file which is basically a function data structure template. It's not an end file, but it's basically a prototype that declares all of the entries of this data structure. And as you can see, it has, if you ignore these for now, on the bottom, it has the same fields or similar fields to your debug float array Mavlink message. So you have your stamp, you have your ID of the message, you have the name of the message. In this case, this name refers to debug array message name, or how should I interpret, or whatever you choose to interpret your data. Like this ID and name refers to, again, internal ID and name of the debug array. There is system ID, comp ID, and message ID that is part of the Mavlink protocol itself that is used by Mavlink to understand what kind of message is that, because you're always sending this. And for the Mavlink to be properly messaged, to be properly decoded, it needs to know, okay, I'm decoding debug float array right now. I have an ID of message ID of 350. I know this is debug float array. This is how I'm decoding. This is its payload. So this payload itself is this, or everything shown here, the payload. It also has name and array ID, or just ID, that is written in here. So just don't confuse these at all with Mavlink stuff. Forget about it. We just took it out of the payload. The Mavlink itself doesn't care about anything inside over here. All right. So this is, again, debug array message of the PX4. This is what we have sent. We can set all of these entries to whatever we want, except for timestamp. I mean, this is something that is getting filled internally by the PX4. And this is also the reason why you see this over here. When we talked about inputs and outputs, for everything to function correctly, you don't, I mean, PX4 documentation, if you read it correctly, it tells you have to provide a correct stamp for using the internal clock of the PX4. I think in the beginning I did not do that. It can cause some problems, although it may appear that it works just fine. But if you want your logging, all of the other things to work correctly, especially such that you can interpret it properly, you would want to write the timestamp and write the timestamp correctly. I did not write the timestamp from the Simulink model. I used, basically, I'm writing whatever inputs I'm receiving, because all of this stuff in the Simulink model is essentially executed consecutively, right? You have your inputs being read, you're evaluating your control system, and then you're writing the outputs. So I'm simply taking the same stamp of all of the inputs, because it's just one timestamp. It's a single message. It makes everything convenient. That timestamp is being used for all of the outputs, so you can easily match what inputs have produced what outputs. Again, two reasons: for convenience of data analysis, as well as making sure that I'm using the correct format and correct timestamp relative to the internal PX4 clock. I haven't found any way to get timestamp generated inside of the Simulink using built-in tools, such that that's the timestamp that matches PX4 internal clock. So this was also the only way I could do it. All right, so let's get back here. Yes, all right. So this timestamp, just assign it for all of the output messages that are being generated from the Simulink, and you should be good. Name, probably not so important, or although again, I'm filling that in for readability, just understanding of what it is in case ID doesn't match or you forget what ID is what. On the ground, you see number, of course, because ID is just a number. This is an actual string. Name is a string. So, and this is what these data entries of the debug array are. These are just some static defines that cannot be changed. You're not even going to see those, I think, unless no, you can't, but you cannot write to them. And the reason for that, again, they're just static. That's just how it is. But basically, these define different types of IDs that I'm using internally. Sorry, these IDs, array IDs, for decoding and encoding, because I need to know, since I'm using the same debug array, I need to know what is this debug array, because I have I have 6 different debug arrays that I'm just calling different, because they mean different things, but they are the same data structure. And when I'm interpreting them, I'm using these IDs to differentiate between them. Basically, how I have defined them in the PX4 firmware, and you see that the inbound ID is 200. So whatever debug array that we are getting on the ground, for example, if The ID here is 200. We know it's an inbound message, or inbound debug array, or whatever we can call it. 250 would be inbound control, and so on. So all of these have their own unique IDs. Yes, and just to again reiterate, the data structure is debug array dot message. It's getting converted by PX4 when you're compiling, and there is actually a C structure called debug array underscore S structure. It's similar to MATLAB structures, and what happens is that I have just inherited that data structure and created multiple instances of that to simplify, because that is a lot nicer to be integrated with the with MATLAB, and specifically UEV Toolbox. That works fine and you don't run into errors. If you add a new message, meaning you add a new file, like not debug array, but if I were to call like SM, like Simulink control mod message, well, that will cause some compile errors and some incompatibility on the MATLAB side, because it assumes a certain number of messages, and you would have to go and modify the toolbox, and it's just a pain. It's a pain. You can do it, it's just a pain to do it, and I decided to completely remove that step altogether. It's far more convenient just to use the existing data structure. But as what I'm showing and highlighting here, I'm creating multiple instances of those. So you see how there's this Simulink inbound, outbound, and all of these instances. And these are separate memory. I mean, these are literally objects, C++ objects